Okay, let's continue with the single phase half wave rectifier with the resistive, inductive plus back EMF. Okay, so this is the condition when you have this back EMF conditions. It's actually when you drive or your load is actually a DC motor. Okay, so in that DC motor, there is actually a back EMF which is usually determined by the rotations of the motor. So there is always a back EMF exists in the motor. So therefore, when you put into the circuit, the equivalent circuit will be the supply voltage together with the back EMF as well as the diodes and the load R plus L. All right. So let's look at what happens if you have that back EMF in the circuit. Okay. So let me make it large. Right, so there you are. So if you look at the waveforms, okay, so the condition is for you to be able to force the current to flow from the supply to the load is whenever you have Vs. Okay, so whenever you have Vs which is greater than VDC, isn't it? Okay, so before that you will going to see that the output voltage is greater than Vs. For example, in this point, okay, if you consider at this point just above the positive, just zero crossing, above the zero crossing there, you're going to see that of course the output voltage, the back EMF, which is 100 volt here, will be higher than the supply voltage. Okay, so even though the diode is actually experiencing forward bias because the supply voltage is positive. However, since the back EMF is greater than the supply voltage at this instant, okay, and therefore diode will not be turned on. Okay, so the diode will not be turned on, and therefore the current will be zero. So there will be no voltage drop here. However, if you measure VDC, then VDC will be equals to the back EMF, which is 100 volts. So that's why if you look at the waveform of the output voltage, when in the conditions of the back EMF is greater than the supply voltage, you're going to see that the VDC equals to 100 volt. So that can be clearly seen here. So I can enlarge it. Look at that. So the output voltage exactly equals to 100 volt, which is the back EMF. Okay, right. So then, whenever when we have the condition of when we have that particular point, if we superimpose into the supply voltage, this is the point whereby the supply voltage is now greater than the back EMF, and therefore current now start to flow in the clockwise direction. Therefore, so diode will be appear as a will be turned on, and now it will appear as a short circuit. Okay, so in this point, then VDC will be connected or equals to the supply voltage. So after that point, after that intersection, then you're going to see that VDC actually follow the supply voltage. Okay, and then when it goes into the negative half cycle, the cycles repeats as what we did explain in the previous section, which is a resistive inductive load, and therefore output voltage will still copy the supply voltage until current goes to zero. Okay, so when you have the current goes to zero at this point, then again diode will be turned off. So diode will be turned off, and there will be no current flow. Therefore, there will be zero voltage drop across R and L, and VDC will be equals to back EMF again. So in this form, we have this condition whereby during negative half cycle, after the current goes to zero, then you see that the output voltage equals to 100 volt again. If I can zoom, then I can see that the output voltage become 100 volt until you repeat the next cycle. Right? So that is very much how to explain the circuit. Okay. And right, so now we have to derive for the output voltage equation. You can read on the explanation here as well as listen to my explanation. Okay, so again, we are interested in looking at the average load voltage. So it's always integration of 1 over t. Okay, integration of 1 over t, 0 to t VDC, the output voltage, equal, this is actually the general equation, and it is always convenient for us to change that into radian, right? And therefore you have 1 over 2 pi, and now you have to integrate from alpha to beta. So look at the waveform again. So you need to integrate from alpha to beta, and the rest of the waveform, because this is a rectangular or the a rectangular waveform, okay, this and that is actually the area under the curve is only a square waveform. Okay, so you don't have to integrate the but you have a area 1. I put it here as area 1 and area 2 here. Okay, so for area 1, if I can zoom again, okay, so area 1, for area 1, you just multiply the height, which is 100 volt, the back EMF, whatever voltage here, multiply with the angle in terms of radians here. So that would be the alpha, isn't it? Yeah, this is alpha. So alpha is actually the point or the angle, the intersection between supply voltage and the back EMF 100 volt. So you can equate supply voltage and back EMF, which is 100 volt. Then you can find alpha here, the angle whereby it intersect between supply and back EMF. Okay, so if you want to get the area, you just simply 100 volt multiply by whatever alpha here, and for this second area number 2, it will be again 100 volt multiply by, so we know now this is beta and this is 2 pi, so the length or the we have height and also the width. Okay, so you just multiply between 100 volt multiplied by 2 pi minus beta, so that will give you this length or base here, isn't it? Okay, so that will give you the area under the curve, and therefore if you look derivation, so you have area 1, area 2, and then at the center you have alpha to beta. So it's simple, simply v pick sine theta d theta. So you solve that, and finally you find out the output voltage equals to this, VDC equals to 1 over 2 pi E alpha, the rest. Okay, you can find that. That would be the equation. I think you have to complete the equations here. Right, so you just simply integrate, and then you put in alpha and beta, and then you get to what is the value for that equation. This is not complete actually, so I have to change that and complete. So you find yourself what will be the last equation for that VDC, the average load. So if you want to get to determine where is alpha, you just equate V peak sine theta as sine alpha equals to E back EMF, and then you can find alpha from this equation. And now for beta, again, you need to obtain the current equations. Once you obtain the current equations, then you'll be able to find the beta in the circuit, right? So for this current, okay, if you look at the current again, okay, if you look at the circuit again, to find the current in the circuits, we have to consider two conditions, which is the force response. All right, the force response is mainly due to supply voltage as well as the VDC here. That will be the force response. Okay, and the other current is actually due to the natural response of the circuits. So that means it's only contributed by this inductor. Natural response is whereby the supply voltage and the back EMF here is deactivated. So you short circuit the supply voltage, and then we look at the current. So this is very much similar to what we did in the previous R plus L section. Okay, so just refer back to the note to determine what the current. So you have to consider force response and force response, and also the natural response. So for force response, you're going to find two case. All right, so I mentioned here IF1 deactivated. So you have to consider one source at a time. So for the first one, you deactivate the, you're going to deactivate the DC source here. So you just short circuit, and therefore this is very much similar to the section before when we have supply voltage R plus L, and that gives you the same equation as previously presented. And for F2, the second source, which is from the DC, you just simply we're going to have this circuit, simple circuit, R plus L, deactivate, you short circuit the Vs, and that's why you have only have E voltage, and therefore for this DC voltage, L will be, the voltage across your L will be 0, because there will be no current change, there will be voltage will be 0, because V equals to L di over dt. So since there is no current change, therefore it will be 0. The current I equals to yes, the current. Okay, so there will be no current, there will be no voltage drop across L. So what left is only IF2 equals to negative E over R. So it is in the opposite direction, and the current IF2. So therefore, the current IFT, the total force current, equals to IF1 plus IF2. So this is from the previous section, and then minus E over R, and you combine with the natural response. This is what you're going to obtain. So this is very similar to 4.27, the previous explanation done in this previous section. So you just refer back, and you get the equation equals to AE to the power of E R over LT, and you combine, and then you know that if you look at the equation, the waveform again, the current will be 0 at 2 points. The first one will be at alpha, and the second one will be at beta. Okay, so you can find the value of alpha using this equation, and therefore you can find the consonant, the coefficient of A by using that information, and therefore you have the complete current equation equals to this one. Okay, so this is the complete equation in terms of time domain, and you can change that to in the radian, whereby omega t equals to theta. So this will be your long equations. This is for your knowledge. Normally we don't test you on this, right? So again, you have the equation here. So if you want to find beta, so you need to change this should be theta, right? So this should be, this is not t, but this is theta here. I need to correct that. Okay, so I theta equals to Vp over Z sine beta and the rest. Okay, so you can test this equation and try to simulate and then verify your answers. Okay, from the simulation you can find the beta by using the simulation, and then you can try to compare with the theoretical calculation as what we did before using this equation for the back EMF, and try to compare between your theoretical calculation as well as the PSIM. Okay, so just quickly on the PSIM, right, if I can show you the PSIM simulation. So we have VDC over 100 volt, and then go to run the simulation. Okay, so just put VS and VDC and make sure that VDC is bold, then you get that waveform, isn't it? So you can find this beta. How to do it? You just measure the delta t, or the time difference between 0 and this beta here. So you will find delta t. See, so you will get delta t there, the time, and then you can do the change that, convert that into angle, whereby we know that for the time, we know that for 0.02 second, that will be equals to 360 degree. So therefore, if you have a delta t, whatever delta t that you have, you measure from the waveform, then that can be converted into degree by using this equation, delta t multiplied by 360 degree, and then you're going to divide all with 0.02 second. So that will give you the beta in degree. Okay.